Waiting for these guys because it may take them a minute. I did want you guys to have a chance to try this out. No, that's gonna happen. So I've got here just a solenoid, the wires wrapped around, going around and around and around there. I've got it hooked up to a power supply. It's pretty high. It's on 12 volts. So there's a significant amount of current going through there.
Should you touch it?
Hmm?
Should you touch it?
Yeah, you can touch it. No problem.
Is it on?
Yeah, it's on.
Okay.
It's definitely on. That would be bad if it was not on. And I was like, yeah, you can touch it, and then turned it on. So anyway, I want you guys to be able to feel it. Remember when current's flowing through, it's supposed to have a magnetic. I think that was your question, right? Could we be able to feel it? Okay, well, there you go. Feel it. Everybody can have a chance. Try both sides, and yeah, you don't have to hold the wipers. One side works better than the other, so put it in just a little bit, flip it around, and then try it on the other side. You can definitely feel a little bit of either attraction or repulsion as you put it in there.
I don't know, maybe my senses are broken. I didn't really feel anything.
Not while you're holding it in there. Let me see. Oh. Yeah, that one's not really doing anything.
Everything was a hoax.
Yeah. These are basically the hold on. I'll find you another one that works. Either that or we'll remagnetize them. And not hold the magnet. Get your wipe on. When it's opposing, you can't feel it very well, but when it attracts, you can feel it just a little bit pulling.
Oh, yeah.
It's not super strong, but you can feel it.
Highly attractive. Not highly attractive. I don't know if I did south that side.
Ooh, yeah. The attractive side is definitely strong.
I'm acing AP
That
Physics
one you
too,
would be
people. It's south that side, north this side works.
All right, awesome. Come on up. If somebody else wants to try, everybody just grab a wipe, have a feel. Everybody give it a try. You can feel it. It's kind of cool.
Why am I like failing? I don't know if I
Just slightly.
I don't know if that's just me.
You have to put the sound.
I don't know.
And kind of just like let it rest on your fingers.
It could very much be my imagination. Okay, I think yeah, it's like pulling it a little bit.
Just
Oh, there it is,
Yes, yeah. And the north is better on the other side. The attraction is better.
It kind of just like makes it faster.
Yeah. It just, you can feel it pull on it. It's not gonna like rip it out of your hand or anything.
I don't know why there's a 35 kilo.
You can see it like when I let go of it.
Oh,
Like, it's in there.
so satisfying.
Anybody else? Come. Grab a wipe it off. Hi guys at home.
I think some people are still in the waiting room.
Yeah. I'll let him in eventually. Tarek's supposed to be here anyway, so that's what he gets. I guess I'll let everybody else in.
I understand what am I not allowed?
So guys at home, just so you know what's going on, they're doing the magnet and the solenoid, feeling the magnetic attraction of the circuit there. What you guys did, what Blue Group did last time. So So give him a moment. Anybody else?
Yeah, oh, and glue, they use plastic bags, let me put a tree on it, so that means it's not. Totally not just a normal plastic bag, which they put a picture of a tree on.
Not like in the supermarket, but in like stores. Yeah.
But they're thicker now, right? Which is definitely better for the environment when you use thicker plastic bags.
I don't know, it seems pretty normal to me.
Anybody else? Before I turn it off. Last time I forgot to turn it off. It was running for about an hour and it did get really hot.
Does
It's
it glow
warm.
orange and start melting?
No, but that would be really cool.
That would be really cool. Yeah, that's why I asked. but-
No, sorry, not that cool. All right, I think we let everybody in that's out right now. Okay. Nobody else? Okay. In case we'll put away that. All right. So today we're going to be starting on kind of our last little segment. Of electricity and magnetism. It'll probably take us a couple of days, but this is kind of the last two big ideas. We've been doing all the magnetic field and forces on a charge, on a wire, right? So today we're going to be looking at what we call electromagnetic induction, all right? And I guess we'll start with induced EMF, all right? So let's consider this. We're just gonna go straight into it today. If we have time later, we'll answer questions. But I think we're kind of at the point where it's probably more valuable to just look at something new. Plus, I'm really excited about this. This is fun stuff. All right, so picture this. We're going to take a metallic rod or bar or whatever it is. It's not magnetic, just metallic. Okay, so it's a good conductor. It's in a magnetic field. All right, and we're going to take this metal bar and we're going to move it over to the right. Okay, constant speed, change in speed, doesn't really matter. Okay, but it's going to move over to the right in this electrical field, magnetic field. This is magnetic field. I guess I should clarify magnetic field. What's going to happen to the metallic rod?
Would it get charged?
What do you mean, would it get charged?
Would it gain a polarity?
Would it gain a polarity? Okay, that's an interesting question. Why?
Well, the magnetic field has to, have induced or not induced, be related to a perpendicular electric field, right? So if the velocity is perpendicular to magnetic field, which it is because it's moving to the right, then it would have an effect on that bar.
Okay. So Akrit's recognizing that there are positive and negative particles in here, right? Throughout your rod. Which right now, when initially they're all kind of in the same place, right? You got your electrons floating around, your protons, and everybody's kind of happy. But as you start to move, Think about what's going to happen to those electrons. The electrons are moving to the right. There's a magnetic field, as Akrit says, into the page, perpendicular. What's going to happen to the electrons? Electrons are going to receive a force downwards, right? I'm using my right hand for those at home that can't tell because of whatever. Right hand, which is the positives, but we know the positives aren't moving because those are the protons of the actual atoms of the thing. So they're not going, but we know the electrons can go. And so as we move on, we're going to get excess electrons down at the bottom. The pluses are going to stay where they were, however many there were, but the minuses are going to congregate down at the bottom, giving us kind of a dipole, right? With a negative charge down at the bottom and a positive charge, net charge, up at the top. Overall, it's still neutral, but the individual pieces, you're going to have positive up top and negative on the bottom. Now, if there's a difference in the charges, what else can we say? What are some of the other things that we know based off of the fact that there's a difference in charges? Think about all that you know about electric fields and such. I know it's a general question, but sometimes those allow you to think a little bit more freely.
If no one else is speaking, I might as well go again. Would there be a potential stored in the metal bar?
Yeah, so we're going to have a potential difference, right, between the top and the bottom. So therefore, you're going to have some potential energy stored there. Not only that, but there's going to be an electric field, right? Yes, as you're moving, there's going to be a magnetic field, a magnetic field in. That means the electrons are going to feel a magnetic force downwards. We already talked about that. But what happens is we start to load electrons down here. Are they going to want to just keep going down to the bottom? You're still going to have that magnetic force downwards, but what opposes that? You're going to have an electric force upwards on the electrons because you have a negative down here and a positive up there. And so the electric field is going from positive to negative. Which means you're going to get an electric force upwards on your electrons. And when those two balance out, then you're going to have an equilibrium. Now that equilibrium is going to depend on several things. What are some of the things that that equilibrium might depend on? Think about your electric fields, your magnetic fields, your electric forces, magnetic forces. What are some of the things that that equilibrium state might depend on?
Velocity of the bar.
Velocity of the bar. Sorry?
The amount of electrons.
The number of electrons. What else? Okay, so kind of the conductivity of the material that allows those electrons to move. Okay, possibly some conductivity there. I did say at the beginning it was a conductor, right? That's important. Otherwise, the charges aren't going to move. They'll just stay neutral in their places. What else? We're actually going to do a formula for it in just a second, but I'm curious to see what you guys will come up with first.
Wait, what are you trying to figure out?
What's going to determine, the separation of those,
Oh, length? Okay.
possibly length?
We're determining the separation of the proton and electron.
Well, to what degree they're going to separate, right? What's going to determine the balance of this magnetic and electric force really is what we're looking at, right?
Newton's third law.
Newton's third law?
Oh, that's stupid. Forget anything I said.
Newton's third law. Everything you said, so should we like rewind
No,
15 minutes? Just the last 3 seconds, all right.
No, I said the stupid thing 3 seconds, more than 3 seconds ago. So the last like minute.
I don't remember what you're
Starting
talking
now.
about. We rewinded.
Okay, nice.
Anything else? Anything else that might affect the balance between that magnetic field and the electric field here?
What is the magnetic field strength itself? Like not of the bar, but of the magnetic field.
Okay, the actual strength of B. Okay, all right, that's good.
Isn't that dependent on velocity?
Sorry?
Isn't the strength of B dependent on the velocity of the bar?
The strength of the magnetic force is dependent on the velocity of the bar. Yep. But the magnetic field, we can just set that. Okay. So let's see if we can come up with a formula. See if we can come up with a formula that relates those two. So we want to find this equilibrium place, right, where the magnetic force is equal to the electric force. Yeah, give me some equations. Sounds like a great idea. Let's use some equations we already know.
The magnetic field equation is QV times V. And the electric field is K Q1 Q2 over R squared.
And then I guess we're finding the distance. You wanna
Now, I want us to be a little bit careful with this one. I've written it down, but what does this apply to?
no, that's the force. No, sorry, 2 charges, right?
It's the force between two charges. So it is electrical force, but remember, this is Coulomb's law, and we really only want to use it if we're looking at 2 charges at a time. I'm a little bit happier with that. So the electric field times Q.
So then if you're trying to find that equilibrium point, we have to, I guess we could do like V equals delta X over T and then solve for delta X. I don't know if that is. But we
Delta
can go ahead and
X.
cancel Q, right? And then get our,
No, we can get rid of the Q's there. So we've got VB equals E.
and now maybe you can do that. I don't know if that's.
Can we maybe find this? Akrit was talking about the fact that we would create a potential difference there, right? So maybe let's see if we can get that. What is the potential difference that would allow these two to be the same?
Well, we have the equation E equals the Canadian potential over a change in R.
Like that?
Yeah.
So then we could say V equals, that's a big V, potential V equals V B R. What was R?
Radius.
Radius? Does it have to be a radius necessarily?
It could be just the length.
Yeah, it's just a distance, the distance between where your positive and negative are, right? So that would be length.
On the very top to the very bottom.
Pretty close,
Yeah,
not
like in the
exact,
middle of
but
the
it's a good estimate, right? Yeah, so you're right. If we're looking at length, it may not be perfect, but hopefully it'll get us pretty close. If you'll notice in your formula packet, if you got a formula packet, pull it out. Is there a formula that looks something like this? Probably not those same letters. Which one is it?
Bottom is right, and then around the board, B times L times B.
B times L times B.
Yeah.
There you go. So you'll notice magnetic field, velocity of the rod, and then the length or the distance between the two ends. Okay, so this is one of the formulas in your packet. Guys at home, am I staying on your screen? Looks like I'm doing a pretty good job so far with that at least. That's right. So basically we just derived that formula that's in your packet. Okay, yes, it is there so you can use it, but it is useful to be able to think through, just like you guys were thinking, setting the forces equal, thinking through, force. We want to make sure to not use the Coulomb's law. We want to use the other electrical force because it's not just two charges, right? Those are good principles to kind of think through as we're setting that up. Any questions about this so far? All right. Isaac, what would happen then if my bar or rod was placed on top of two conducting rods? So these are also metallic, and then connected. What do you think would happen there, Isaac?
Well, it would make a circuit, and the magnet thing would be a battery.
Yeah, you'd
or a
essentially
cell and something like that.
Yeah, because you'd have a positive here and a negative here. The magnetic force would continue pushing them out, but now they have a release place. The current can go from positive to negative by going through your resistor, your light bulb, your motor, whatever it is. And so as long as we're moving this bar through the magnetic field, we then get current. Okay, now this is one way to consider this circuit. We're going to look at it in a different way, hopefully near the end of class, once we get a little bit more physics kind of under our belts. But yes, by moving the bar, we can create a current, which then allows us to run the resistor as long as the bar keeps moving. What would happen if I then took the bar and started moving it in the opposite direction? Because I can't move on that way infinitely, right? Eventually I'm going to get to the end of the metal rods. What would happen if I then took the bar and started pulling it back this way instead? All right, I'll give you a minute. Think through that. What would happen if we start going back the other way? I know, isn't it great? David, as soon as you're ready, give us an answer, man. What do you think?
I'm really not sure.
You want to make a guess? You want to try to reason through it with us, or you'd rather phone a friend?
I'd rather have some help. I don't.
All right, who you want to call? Say Ghostbusters, I'm gonna slap you.
Rom.
Rom, all right, Rom, help us out, man.
You phoned the wrong friend because I have no idea what's gonna happen in another direction as well.
You just lost your $1 million.
Yes. Very sad.
What's gonna happen as we bring the rod this way? We're pushing it that way. The electrons are gonna move that way, right? Magnetic field into the page. Where are the electrons going to go? Ram and David, you can say it at the same time.
Damn.
Or not say it at the same time.
Is it? Then go down?
I thought you started to say something. One of you
I
did.
feel like it would go down or
So we've got the magnetic field going into the page. Right hand rule.
But then it's
The bar is moving this way. Magnetic field into the page. So my right hand thumb is down. But that's what would happen to the positives. So what would happen to the negatives?
could they go in the other direction?
They go in the other direction. That's right. Very astute. So the negatives are still moving that direction, right? But the force on the negatives is going to be upwards. And so the negatives are going to move up to the top. The positives stay at the bottom. Right? There's still everything's moving in that direction. I'm taking this bar and moving it that way. Everything's moving that way. Positives, negatives alike. The force on the positives is going to be down, but they can't go anywhere. But the force on the negatives, because it's a conductor, those free electrons, they're going to be able to go up. So the electrons then will be able to flow, meaning the current will now go the opposite direction around the loop.
So you said that, okay, so you said that this is like the force, right? And the force would be up, or the force would be down. So it's possible to have an alternating current where it doesn't even go to like less than what the initial was. Because you move it to the right and then the voltage increases, you go to the left, it goes back to zero because the force was opposite to that. So it just cancels out.
I see what you're saying. But what would happen as soon as I stop moving it?
Would the current stop?
The current would have to stop, right? Because eventually I'm going to use up, there's no magnetic force anymore, right? When I stop, this force stops. The electric field is going to balance things out. The only reason there's electric field is because I had a positive and negative end. But as soon as I stop and that magnetic field, that magnetic force stops, because remember there's only a magnetic force if they're moving in the field. So as soon as I stop, this is going to flow until it's balanced. Kind of like the capacitor idea where we had the positive and negative, but they're just going to flow back until it's neutral again. So as soon as I go back in the opposite direction, I'm going to have a negative potential. So it's not going to be zero. It's not going to go back to what it was originally. It's going to go negative. If I go at the same speed, it's going to be negative of what it was before. Other questions? All right. Let's try calculation then. We're looking at number 11, example number 11 from the student notes. Let me see, I guess I can put it up here for those that are in the class. I do have it open. Let me move it over. Share screen. All right, here we go, number 11. Hopefully at home you guys can see that. Working through number 11, we'll work it together. You're welcome to start it if you want. Oh, sorry, I meant to go back to your blue things. So we recognize that the magnetic field, the length, and the velocity were the things that mattered in creating that balance between the electric force and the electric field. All right. Let's try to do a problem. So it gives us L is 0.10 meters. Gives us that the speed to the right is 2.5 meters per second. Gives us that the resistance of the loop is 0.030 ohms. The magnetic field into the page is 0.60 Tesla. All right. Can we find first the EMF? Now what this is we call this the induced EMF because it's being created because of the rod's movement through the electric field. So how would I find the induced EMF? Aisha?
Well, we have the velocity and we have the magnetic field. Okay, so then we could just use that equation and have everything.
Good, we got that equation.
0.1 times 2.5 times 0.6.
That's right. So straight up, we can use that formula that we just created because it is in the formula packet. So we go 0.60 times 0.10 times 2.5, and we get the induced EMF.
I believe that's 0.15.
0.15.
I think so.
Anybody else? Zaid got the same thing? Guys at home, I need confirmation just in case calculators at home work differently than calculators in the classroom.
Yeah, I got the same answer.
Ram got the same. All right. I guess they're working the same. Perfect. Okay, so that was the induced EMF. So that's the difference in the potential at the top and bottom of that rod there. Okay, the second question to ask is find the induced current. What would the induced current be there? How would I find that?
Use like V equals IR. That work.
Yeah, because if the potential across here is 0.15 volts, then that means that the potential through the wire also has to be 0.15 volts, right? According to Kirchhoff's laws, you go all the way around a loop, it's got to be 0. So we go V equals IR. And so then we can go 0.15 equals the current times the resistance which was given to us. And we should get current equals
5, I think.
You okay with that? All right. All right. How about the next question? So those were a little bit easier, a little bit straight up. How about the next one? The force acting on the rod. What force has to be acting on the rod in order for that to happen?
Magnetic.
Magnetic force? Magnetic force. All right. Yes. equation you want to use there? QB. Okay. That one?
I don't know what we would use for Q.
I don't know either.
Something like F sub E equals Q. Yeah, F sub E equals QE. So we can rearrange that. We can say that F sub E over E equals Q.
You want to set the electric force equal to magnetic force? Is that what you're saying?
No, I want to substitute
Wait,
the electric force.
if we do
And-
magnetic force, it would be electric force and we cancel out the Q.
It would.
But then we won't get the.
But would we be talking about the rod now, or would we be talking about the electrons in the rod?
We cancel out the Q's.
No, if we set those two equal. When you say we're gonna make the electric force. Yeah. So remember that electric force equals magnetic force was for the guys in here that were being forced to the ends and maintaining that EMF, right? Maybe let's ask this question first.
I need 0 because of all.
Okay, so that was the question I was gonna ask. Ockert said, well, the velocity is constant speed, so why do I need a force? So that's the question. The velocity is constant. Obviously, the net force is 0. Is it necessary for me to keep pushing on it? Are there any other forces in play?
Well, D says that mechanical power is needed to keep the net.
So if you look ahead, you say, yes, there is a force needed there, isn't there? Why? You were close. What were you thinking about earlier when you were talking about this magnetic force equals QBB? What magnetic force were you looking at?
I was thinking about the fact that there is a magnetic force in there's a field, and then there's also a current that's running through the wire. So those two should be acting on each other. And since the metal rod is in series with the current,
Okay, so we're getting a little bit deeper here, right? Before we were just saying, we moved the rod and a current's gonna start. But what happens when there's a current going through this rod, going through the magnetic field? There's gonna be a force on that. Okay, so it's the next layer. It goes a little bit deeper. So which direction, let's see, we said the velocity is going that way, magnetic field that way, so positives go that way, negatives go that way. Which direction is the current going? Like this, right? Okay, so current's going that way. Magnetic field into the page. What direction is the magnetic field on the wire now that there's a current moving through there? To the left. So what do I have to do to keep it going at a constant speed? I've got to apply a force. Now that should make sense because you can't get free energy, right? If you were to say, oh yeah, that thing's just going to continue along at a constant velocity, I don't have to push it. Where's the current coming from? Where's all that energy coming from to get that current to flow, right? You're not changing kinetic energy. So where's it got to come from? Well, there has to be something else. Well, you have to be exerting a force, putting energy into it in order to be able to get energy out of it, right? So now we got the idea. We understand that, yes, as I move the rod, that exerted a force on the protons and electrons, getting them to start moving. But now that they're moving, up and down. Now they're not just moving side to side. Now they're also moving up and down, which now exerts another force, which is now to the left. Can we find the magnitude of that force to the left? It's very close to QVB, but it's not QVB because we can't find the Q.
What about this equation right here?
Adit, you're about to raise your hand too. Is that what you're gonna say?
Yeah, yeah.
I figured it was, but I hadn't heard from Adit yet, so we'll.
No worries. Trust me, I do.
That one, right?
You know, Mr. Bywater, kind of a tangent, but in 6th grade, Mr. Campbell said I could only ask 100 questions in the semester, and then that's it. I couldn't ask any more.
Did he actually count?
That's only like 3 a day.
Exactly.
Did he count?
I think I expanded most of them in the 5th grade.
Yeah. I was waiting for you to say that he told you could only ask 100 questions in a period, and you surpassed that. He stopped you. That would have
Do
been
I really
awesome.
say that one?
That would be awesome. No, you don't quite get there here, but that would be really awesome. All right. So the magnetic force due to the current is ILB. Okay. So can we find that now? We got the current, right? We got the current, 5.
And the length is
We got the length. And we got the magnetic field.
It's 3.3.
Now, if I want to keep it at a constant velocity, if the magnetic field is 0.3 to the left, accurate, you can say it now.
Oh, Newton's third law?
Yeah, Newton's third law. 0.3 to the right.
I really hope someone's wearing earpods at home. AirPods, listen.
All right. Everybody okay with that? Any questions?
But why would it be a magnetic field force that way? If the magnetic field force.
The magnetic force is that way,
Yeah.
which means that I have to push the rod. There has to be something mechanical pushing the rod, otherwise it can't be
Would that be
maintained.
considered a magnetic force?
This is a magnetic force in that direction,
Oh,
Right.
Okay.
but we're saying because of Newton's third
You
law,
have to apply a force that way.
there has to be an equal opposite force.
So that would be to the left.
This one would be to the left. The magnetic field is to the left. Yep, that's exactly right, because the current's flowing up into the field that is to the left. But the answer to the question is that we need to apply a force of 0.3 newtons to the right in order to maintain that velocity.
Since now there's a current going through the wire, doesn't that mean that the wire now also creates a magnetic field for the phone?
It does.
And then you're not like getting mixed up by like which magnetic field to input into that equation.
But remember, if this is creating a magnetic field, it doesn't affect itself.
Oh yeah, because of the yeah.
Because then you'd say, oh yeah, but then this, and then that's going to change the current again, which is going to change. Luckily, it doesn't go any further than that. Yes. Awesome. Awesome. Mechanical power, how would we do that?
Could use power is force FD over V.
FD over V, not over V, right?
Yeah, because it's F delta T. We don't know how to do that, so we say that delta T is V over V.
F delta T, isn't that impulse, momentum?
Oh yeah, maybe that explains a lot. Actually.
That does explain a lot.
Oh no, then it's okay. So then we can say that it's
Sorry? T equals I delta V.
But I thought we couldn't use electric here because we are applying a Newtonian force, right? Like a kinematic force is what I mean to say.
Let's see. Let's see if we end up getting the same thing. That's a very good question. So if we take the current, which was 5, right, times our delta V, which was 0.15. Then if we use the electronics way, we get 0.75, right? Am I still staying on the, just barely? All right, now Akrit's saying, but isn't this a mechanical energy? Can we use the electrical power when we're talking about a mechanical force and a mechanical energy, a mechanical power? Any ideas how we would do that?
Oh, I have one.
Time would be nice. We don't have a time though. But why? Why? Why would a time be helpful?
Mechanical power is work over time, and then work is easy. We have that, I guess. We know the force that we're.
We know the force, but how is that connected to work?
Oh, because we're also pushing it a distance.
Oh, so you're saying that power equals force times distance over time?
Yes. Oh, there you go.
Ah, so we don't need the time because we got the distance over time, which is velocity. So we can do that. So we can say that the power equals the force times the velocity. So the force was 0.3 and the velocity was 2.5. What do we get?
Well, mental math. 0.75.
Wait, so the electrical one worked? How does that make sense? I thought it wasn't supposed to work. Or is it? Any ideas? It's a huge concept in physics.
But is it the second law of thermodynamics?
What's that?
Law of conservation of energy.
Law of conservation of energy, right? The electrical energy that you are getting out must be equal to the mechanical energy that you're putting in, right? We're not considering any thermal energy being lost. And so therefore, yes, the two powers better be equal. The energy you're putting in must equal the energy coming out. Nice. How about them physics? That was great. That was great. All right, any questions? I think we answered all the questions there. All right, we're gonna take a quick break then. When you come back, I got a couple of demos for you, and we're gonna see a different way of looking at this problem. All right, so go ahead, take a break, be back in 3 minutes. Ready to go.
I need to change these people.
So
I know.
think I screwed up the
I don't
law of
even sit in them, I
thermodynamics.
hate them. You screwed up the law of thermodynamics.
What were the laws? Can you remind me? It's been a while. I need a little refresh.
All right, so I forgot to turn on the video when we came back from break, so I'm going to give a quick summary right now. So the first thing we did is we looked at this right here. The solenoid is connected to the ammeter here. You want to come watch this for a second? Pretty cool. What you'll notice is, of course, there's no current flowing through there. It's not connected to any batteries, okay? It's just the wire going around here. Now, what I want you to watch is look at the current meter here as I put the magnet, which is a normal everyday magnet, as I put the magnet inside the solenoid. What did you see? Okay, notice that as it goes in, there's current flowing through the wire, right? As it goes in, there's current, and as it comes out, there's current. But when it's sitting in there, there's no current. Or when it's sitting on the outside, there's no current. Now this is significant. This introduces us to something that we call Lenz's law. Okay, Lenz's law says that when a magnetic field is changing, that a current will be induced that creates a magnetic field that opposes that change. Okay, so as I put the magnetic field in, it's increasing the magnetic field in this direction. So what happens is a current is induced that opposes that change. So the current being induced is going to go around the loop like this, opposing the change, because as I go in, the magnetic field is increasing this direction. So the induced magnetic field is the opposite direction, which means according to the right-hand rule, the induced current is going around that way. Now, as I pull it out, I'm decreasing the magnetic field, right? I'm decreasing because it used to be really strong in that direction, but now that I'm pulling it out, there's less. And so the induced current needs to maintain the magnetic field that was there. So it needs to go this direction now, and so the current is going to go the other way around, which is why one way you see it go positive, and the other way you see it go negative, right? Negative and positive, right? And so you can see that as we put this. So that's Lenz's law. Lenz's law is very qualitative in nature. It says the induced current will give a induced magnetic field that will oppose the change in what we call the magnetic flux. All right. Now, magnetic flux is a new concept. It's not the change in the magnetic field. I know flux makes us think of a change in magnetic field, but that's not actually what it is. Magnetic flux is equal to the dot product, so not the cross product that we had last week. This is the dot product between the magnetic field and the area of the loop that we're looking at. And so it does require a loop. A single wire won't have this phenomenon. All right, so magnetic field times loop. Now, dot product means that we want the part of it that's parallel. Okay, so parallel means BA cosine theta. All right, and so the magnetic flux is equal to the magnetic field times the area of the loop times the cosine of theta. Now, when we talk about the direction of the area here, it's difficult to say a direction of an area. It's defined by the vector that's perpendicular to the surface. And so when the magnetic field is parallel to that, that's when we actually have the highest cosine theta, right? When the magnetic field is parallel to that directional vector from the area. And so that's when we get the strongest flux. Now, flux, again, is not a change. It's an amount, right? You could say it's the number of field lines going through a specific area, right? What is going to increase the flux? Well, if I have a stronger magnetic field, this guy right here, stronger magnetic field means more flux because a stronger magnetic field has more magnetic lines. We then also have the area, okay? If I increase my area, obviously it's going to fit more magnetic field lines. Again, flux is basically how many magnetic field lines we fit. If I have that area perpendicular to the field, or the area vector is parallel to the field, I'm going to get the most magnetic field lines. If I tilt it, then I'm not going to get quite as many magnetic field lines going through that area. Okay, because some of them are going to go through at an angle, so I'm not going to get the ones on the edge. All right, so therefore, this right here, I can change the magnetic flux by increasing the magnetic field, by increasing the area, or by making sure that those two vectors are as close to parallel as possible. Now, again, Lenz's law that we just talked about, Lenz's law says that as I change a magnetic field, that the induced current will create a magnetic field to oppose that change. Not the direction of the field, but how the flux is changing. Now, Faraday's law is very similar to that, but Faraday's law tends to talk about the EMF. It's the induced EMF. Like we were talking about earlier, there was an induced EMF in this bar, and we'll look at that in just a second. So the induced EMF is equal to the change in the flux, right? Is it increasing or decreasing over the time? Okay, so it depends on how quickly that flux is changing. And that's Faraday's law. It's much more quantitative in nature, whereas Lenz's gave us a direction, just a direction of the current, the direction of the induced magnetic field. All right. Now, I did want to talk about this really quick. We talked about this at the beginning of class, the bar moving to the right. We said that because of the forces and other things that it was going to create a current going this way. I want you to think about this. As we move the bar that way, we now are increasing the area, which means I have more flux going into the page. So what is the induced current going to do? The induced current is going to create a magnetic field to balance that coming out of the page, trying to maintain what was there before. And you'll notice that when I use my right-hand rule to create a magnetic field coming out of the page to counter the increase into the page, the induced current is going around this way, which is exactly what we said when we looked at the magnetic field and the forces and all those other things. And so we were able to explain exactly the same phenomena in a different way. The last thing we talked about in class is the idea that this is how electrical generators work, right? It doesn't matter whether, all of those power generating factories somehow generate heat, whether it's burning coal or nuclear power or burning natural gas. It generates heat, which boils water, or usually water, which then that water turns into steam, which turns generators. Now, as you turn those generators, what it's doing is it's either turning a magnetic field or it's turning a wire. Think about this. You got a magnetic field going from here to here, this direction, right? Magnetic field going this way. If I have a wire like this, there's no flux there. So I have a circle, a loop right here, okay? And remember, a loop can be a bar and wires going around there. So it just has to be something like this, flat loop, magnetic field's going this way. There's no flux, no field lines going through my loop. But what happens is it starts to turn. Well, now I start to get some field lines, right? Going from one side to the other, going through here. And as I turn this way, now I have the maximum number of field lines going through there. And then the field lines start to decrease again. So I continuously have a change in flux. If I continuously have a change in flux, then I will continuously have an EMF and or a induced current. However, because it's turning, sometimes the flux is increasing, sometimes the flux is decreasing, which means that sometimes the current's going to go one way, sometimes the current's going to go the other way, which is how we get alternating current. That's why when you plug your thing into the wall is providing alternating current. The wall is providing alternating current because that wire is continuously spinning within that magnetic field. Or you get the magnetic field to spin around the wire and you get the same effect. Hydroelectric power is the same, right? You get water falling over a waterfall, turns the turbines, and therefore you're spinning either the magnetic field or the wire in the magnetic field, and you're continuously creating alternating current. That's it. And that's kind of what we wrapped up with today. Take note of Lenz's law and Faraday's law. We will spend some more time looking at that next class. Hope that was helpful, and I'll see you next time.